We first consider the first part of the analysis of variance in this particular lecture, and later on we will consider the second part. The first thing that we need to know that what do we mean by analysis of variance? By definition, the total variation present in a set of observable quantities may under certain circumstances be partitioned into a number of components. The systematic procedure of achieving this is known as analysis of variance. We know variance or variability is a very natural phenomena. In almost everywhere where we collect raw data, variability is present. Now, since variability is present, we may feel like knowing why this variability is occurring. In order to search for this, we consider what we mean by analysis of variance technique. For example, suppose we have a piece of land divided into a number of plots. Suppose we yield paddy in these plots. Now, obviously, the yield of paddy will not be same in all the plots. For simplicity, we assume that the plots are of all equal size. So, the yield of paddy is not same in all the plots. Now, we may feel like knowing why there is some variation or variance in the yield of paddy in different plots. There may be a number of reasons. It may be that the fertility of the plots differ from one another. It may be that different pesticides might have been applied in different plots, so on and so forth. So if we can identify the effects of these different treatments, for example, fertility, for example, pesticide, etc., then we may find out the reason of this variability. This is basically what we mean by analysis of variance. In this setup, in the setup of one-way classified data, we classify the given data with respect to a single criteria. For example, if we take the yield of paddy in different plots, then we will assume that the plots are classified according to a single criteria, according to one criteria. Suppose that criteria is fertility. So you can see on your slide that different fertilizers might have been used in different plots. So the plots are classified only with respect to one treatment or one criteria, which is fertilizer. So this is one-way classified data, and we will learn how to analyze mathematically a one-way classified data. So suppose there are in all small n observations classified with respect to a single criteria, and we name that criteria as A. So in our example, A will be fertilizer. Suppose A has got K levels. Now what do we mean by K levels? There may be K different fertilizers. K may have the value 3, may have the value 4, and so on. So we have K different fertilizers, say A1, A2 up to AK. That means in mathematically we say that there are K levels of the criteria A denoted by A1, A2 up to AK. And let Ni be the number of observations in the ith group. That means there will be N1 plots receiving fertilizer A1, N2 plots receiving fertilizer A2, and finally Nk number of plots receiving fertilizer Ak. So N1 plus N2 plus Nk, this will be the total number of observations, which is in our case N, small n. Now we come to the model of a one-way classified data. You can see the model is Yij equals to mu plus alpha I plus Eij, where I runs from 1 to k and j runs from 1 to ni. So here we have to explain what are the components in this model. First of all, Yij. It is the jth observation belonging to the ith class. That means if we stick to our example, so suppose there are N1 plots receiving fertilizer A1. So Yij will be the yield of paddy in the jth plot receiving the fertilizer Ai. Mu is the general mean effect. So what is the general mean effect? There will be some property of the soil which is common to all the plots. This common effect is known as general mean effect. Next we come to alpha I, additional effect due to the ith class. Each fertilizer will have some separate effects, some different effect. So the effect of the ith fertilizer in particular will be denoted by alpha I. and there will be an error component, because it is not possible to explain the variability in the full form. That is, we cannot explain fully the variability. There is always an element of chance, an element of error. So this error is denoted by Eij, and we call it a random error component. Why it is random? Because we do not deliberately commit any error. The error always creep in any experimentation. So these errors occur randomly. That is why Eij will be called a random error component. Next, there will be some assumptions on which the whole analysis of variance technique is based upon. Number one, summation Ni alpha I equals to 0. What is alpha I? Recall, it is the additional effect due to the ith fertilizer in our example. And Ni is the number of plots receiving the ith fertilizer. Summation Ni alpha I will then be what? Some weighted sum of these alpha i's. So you see, some fertilizer will have positive effect, some fertilizer will have some negative effect. Like there is a general mean effect. Had not any fertilizer been used, there would have been some yield. So some fertilizers will give yield better than the general effect. Some fertilizers will give yield lesser than the general effect. So summation of this, the weighted sum, summation Ni alpha I, is naturally 0. And we have seen earlier that in any testing problem, there is an assumption that the data comes from a normal population. So here we will assume that the error Eij follows a normal distribution. In particular, we will assume that Eij follows a normal distribution with mean 0 and variance sigma square. This is very important. You see, Eij follows normal 0 sigma square. Irrespective of I and j, Eij follows a normal distribution with a given mean and a given variance. That means whatever be the fertilizer, whatever be the plot, always the distribution will remain the same. Now I said that the data has to follow a normal distribution. So the question was, if Eij follows a normal distribution, will that guarantee that Yij will also follow a normal distribution? Let us go back to the model. You see, in the model, Yij is nothing but a linear function of Eij. So if Eij follows a normal distribution, definitely from the properties of normal distribution, we can say that Yij will follow a normal distribution. So that means the data comes from a normal population, which is an essential condition for parametric tests. Next, we go to the hypothesis to be tested. We want to test whether alpha 1 equals to alpha 2 equals to alpha k equals to 0. That is the null hypothesis, and the alternative hypothesis is not H naught. So the alternative is a vast number of hypotheses. If there is inequality in any one place, that means H naught is rejected. If there is a violation of equality in any two places, then also H naught will be rejected. So encompassing all these alternatives, we write H1 as not H naught. Now here we test alpha 1 equals to alpha 2 equals to alpha k equals to 0. So what is H naught? H naught basically means all the effects, all the additional effects due to different fertilizers are 0. So what does that mean? That means that had there been no additional effect due to the fertilizers, then there had been no variation. So actually we want to know whether the variation is occurring due to fertilizers or we cannot account for this variation. This is what we want to know in an analysis of variance technique. So we come to the analysis part. First, we have to compute the sum of squares. The first sum of squares is the total sum of squares. That is double summation Yij minus Y naught naught bar whole square. Now Y naught naught bar is nothing but the mean, the grand mean of all the observations. Taking into account all the observations, the mean is Y naught naught bar. So double summation Yij minus Y naught naught bar whole square is basically the sum of squares of the deviations of each observation from the grand mean. If you can try to understand, you see, if this TSS is divided by n, then that would have been the variance, nothing else. So instead of variance, we consider the total sum of squares. So it gives us the total variability of the set of observations, the total variability considering all the observations together. Next, sum of squares due to groups. See, we have k number of groups. We have k number of groups, so sum of squares due to groups. That means the variability due to the groups. That is summation y I naught bar minus y naught naught bar whole square. What is y I naught bar? If you look at the formula, there are ni observations in the ith group. So y I naught bar is nothing but the mean of the observations in the ith group. So in our example, it is nothing but the mean of the yields of those plots which have received the ith fertilizer, which have received the ith treatment. So y I naught bar is the mean of the ith group in that sense. So there will be variability. If the fertilizer effects are different, there will be variability between y I naught bars for I equals to 1, 2, etc. up to k. That means y1 naught bar will be different from y2 naught bar, that will be different from y3 naught bar, and so on. y1 naught bar, y2 naught bar, y3 naught bar are the means of the first group, second group, third group, etc. So how to calculate the difference between these means? Again, a sum of squares is required. That is what is SSA, the sum of squares due to groups. There is another sum of squares which is called the sum of squares due to error. So that is double summation yij minus yi naught bar whole square. And we can show that total sum of squares TSS is SSA plus SSE. This is a very important statement. See, there will be variability among the observations. And how do we capture it? That variability is captured by the total sum of squares TSS. Now we are looking for the reason behind this variability. So one part of this variability can be accounted for by the fertilizers, that is by the groups in general. So there are k different groups, so we have k different fertilizers. So the sum of squares due to groups will give us the reason behind the variation due to the fertilizers or due to the groups. But there will be one more part remaining, because the whole of the variation can never be explained by the groups. So one part will remain. That part is SSE, the sum of squares due to errors, which is given by the formula. Once again, I'd like to note you down. That is double summation yij minus yi naught bar whole square. Next, we come to the degrees of freedom. TSS has got degrees of freedom n minus 1. Consider degrees of freedom. We have come across the notion of degrees of freedom in chi-square distribution, in T distribution, in F distribution. We studied earlier. So we will make use of something like that here also. So that is why we have degrees of freedom. So TSS has got n minus 1 degrees of freedom. SSA, that is sum of squares due to groups, has got k minus 1 degrees of freedom. And SSE has got n minus k degrees of freedom. Now it's very interesting. How do we get the degrees of freedom of SSE? If you recall, the relationships between the three sum of squares was TSS is equal to SSA plus SSE. You can see on your screen, TSS is equal to SSA plus SSE. The corresponding degrees of freedoms will also have the same relation. That is, the degrees of freedom of TSS will be the degrees of freedom of SSA plus degrees of freedom of SSE. Now you can see here TSS and SSA, we got the degrees of freedoms. So the degrees of freedom of SSE, how will we obtain? The degrees of freedom of TSS minus the degrees of freedom of SSA, as you can see on your screen. So it comes out to be n minus k. So we have got the sum of squares, we had got the degrees of freedoms. Next, we will consider something called mean sum of squares. So mean sum of squares due to groups is given by MSA, that is equal to SSA by k minus 1. So how do we get a mean sum of squares? By dividing the sum of squares by its corresponding degrees of freedom. So similarly, mean sum of squares due to error will be given by MSE, that is SSE by n minus k. The sum of squares due to error divided by its degrees of freedom. Now there is nothing called mean total sum of squares. Total sum of squares is something that captures the total variability. The mean here does not apply. Next, we go to the test statistic. Since we are testing a hypothesis, obviously we have a test statistic. So here the test statistic is given by T is equal to MSA by MSE. That is the mean sum of squares due to the groups divided by the mean sum of squares due to error. And it can be shown that under H0, that is assuming H0 to be true, this T, the test statistic, will follow an F distribution with degrees of freedom k minus 1, n minus k. Recall, F distribution has got 2 degrees of freedom. So here the first degrees of freedom will be the degrees of freedom of SSA, and the second degrees of freedom will be the degrees of freedom of error, sum of squares due to error. So it will follow an F distribution with degrees of freedom k minus 1, n minus k. Now we come to the test procedure. So we have to, given a data, we have to calculate, first of all, we have to calculate T. First sum of squares, then degrees of freedom, then mean sum of squares, and then finally we will calculate T. So what will be the test procedure? That means what will be the rejection criteria for the null hypothesis. So we reject H0 against H1 if and only if T is greater than F alpha semicolon k minus 1 n minus k, where F alpha semicolon k minus 1 n minus k, you have seen earlier that it is the upper alpha point of an F distribution with degrees of freedom k minus 1, n minus k. Alpha is nothing but the level of significance of the test. Now my question is, why we will reject the null hypothesis if the value of our test statistic exceeds the tabulated value? Why not if it is less than the tabulated value, or in general if it is not equal to the tabulated value? So the question was this: why should test statistic have a value which is greater than the tabulated value to reject the null hypothesis? Let us go back to the test statistic. You see, the formula for the test statistic T is MSA by MSE. So mean sum of squares due to the groups divided by the mean sum of squares due to error. Now see, we have a variability in our hand, which is a natural phenomena. We can't touch it. We just want to know why this variability is occurring. Is it because of the fertilizers, or this variability is a random phenomena? Now see, if it is because of fertilizers, then mean sum of squares due to the fertilizers or due to the groups will have more value than mean sum of squares due to error. That means among the two mean sum of squares, the mean sum of squares due to the groups will have a higher weightage than the other. So since we are taking this ratio, so higher the value of T will mean what? Will mean that the more amount of variability or the more proportion of variability is due to the fertilizers, due to the groups. So that is why we reject when T has a higher value, in particular when T will have a value which is more than the tabulated value for a given level of significance. And finally, what we do, we summarize all these things into a single table, which is very important. This is called ANOVA table. So you see the components of ANOVA table on your screen. This is very important. This is the convention to put these columns in the ANOVA table. First, sources of variation. There are two sources of variations. One is group and the other one is error. And the total is the total variation. So the sum of squares, group sum of squares is SSA, the error sum of squares is SSE, and the total sum of squares is TSS, as we have seen earlier also. In the next column, we have put down the degrees of freedom. And then the mean sum of squares. Obviously, you see, there is nothing in the total row because there is no concept called mean total sum of squares. And then we have the test statistic. One is the observed, that which we will calculate, and one is the tabulated, which is already there in the table. So these components should be there in the ANOVA table. Now we will discuss, for a given data set, what steps are to be followed to analyze a one-way classified data. So step 1, we will calculate the mean for each group, the average for each group. We will calculate the total mean. This is done by adding all the means and dividing it by the total number of means. So if there are k groups, then I will add up all these k means and then divide by k. We have to calculate the sum of squares due to the groups, and then the degrees of freedom, the corresponding degrees of freedom, then sum of squares due to error, again the corresponding degrees of freedom, and then we have to determine the mean sum of squares, MSA and MSE. So next we will find the F statistic, that is the test statistic which follows an F distribution, and using the F table for the specified level of significance alpha, we will find the critical value from the table, and then we will compare our test, the value of our test statistic with the critical value. Obviously, if the observed F is more than tabulated F, we will reject the null hypothesis. So these steps are to be followed in any one-way classified data analysis technique. We take an example. There are 3 types of fertilizers which are used on 3 groups of plants for 5 weeks. We want to check if there is a difference in the mean growth for each group. Using the data given below, we have to apply a one-way ANOVA test at 0.05 level of significance. Now, the data is this. There are 3 fertilizers you can see which are applied. So, we have 3 groups of data. So, this data is to be analyzed. Now, first of all, you see this is a one-way classified data. Why? With the data, there are several number of observations, but these data are classified with respect to a single criteria, which is fertilizer. So, this is again a one-way classified data, the analysis technique of what we have studied just now. So, we have to test alpha 1 equals to alpha 2 equals to alpha k equals to 0 against not H naught. So, here what is the value of k? The value of k will be 3 because there are 3 fertilizers as you can see. So, basically we are going to test whether alpha 1 equals to alpha 2 equals to alpha 3 equals to 0 against not H naught. Again, I would like to emphasize this fact that not H naught will encompass a number of alternatives, a number of alternative hypotheses. Alpha 1 not equal to alpha 2 equal to alpha 3. There is one possibility. Alpha 1 equal to alpha 2 not equal to alpha 3. There is another possible alternative hypothesis. So, there are several possible alternative hypotheses. All these together we call not H naught. That means anything that deviates from the null hypothesis. So, we calculate the means of different groups. Mean, there will be 3 different groups. So, 3 means. So, these 3 means divided by 3 will give us the grand mean. And here the number of observations of the first group, number of observations of the second group, number of observations of the third group. Here these 3 are equal. They are not necessarily equal. They may be equal. They may not be equal. You can see the data again, once again. Here we have equal number of plots receiving fertilizers 1, 2 and 3 respectively. So, which is 6 in all the situations. But there could have been 3 fertilizers receiving 3 plots receiving fertilizer 1, 5 plots receiving fertilizer 2 and 4 plots receiving fertilizer 3. That could have been possible. So, N1, N2, N3 here 6, and as I mentioned earlier also k is 3, the number of fertilizers. So, we first calculate this SSB, that is the sum of squares between groups we can say, because this basically denotes the variability among the groups, the variability between the groups. So, we can denote it by SSB as well. That comes out to be 84, and degrees of freedom is k minus 1, k is 3 in this example, so it's 2. We calculate SSE also. Capital N is 18, so that is the total number of observations. So the degrees of freedom for SSE will be n minus k as we have seen earlier, so it comes out to be 15. Now dividing the sum of squares by the corresponding degrees of freedom, we get the mean sum of squares. So we have mean sum of squares between groups and the mean sum of squares due to error. And the test statistic F will be MSB by MSE as we have seen. So 9.33 comes out, the value of the test statistic. So using that F table, we can find out. So what we have to find out in the F table? You can see, once again I go back to the question. The question says that we have to test at 0.05 significant level. That means the level of significance is 0.05 and the degrees of freedom are, you see, k minus 1, that is 2, and n minus k, that is 15. So we have to find out from the table, we have to find out F 0.05 to 15. From table it can be found out as 3.68. So our value of the test statistic is 9.33 while the tabulated value is 3.68. So my question is, what should be our conclusion? What should be our decision in this testing? So here the test statistic exceeds the tabulated value. So that means the variation due to the fertilizers is more than the variation due to the error. So that is why we reject the null hypothesis. Now here we have to understand one thing. Do we want to accept the null hypothesis or reject the null hypothesis? That means, in other words, shall we be happy if we accept the null hypothesis or shall we be happy if we reject the null hypothesis? The answer to this question is very simple. If we reject the null hypothesis, that means we have found out a reason behind the variability. So if I wish to find out the reason behind the variability, I should be happy if I reject the null hypothesis. But everything will depend on the data that we suspect. If we suspect that there is some reason behind the variability does not occur purely randomly or does not occur due to the error only, then we go for this ANOVA test. We can take another example. The positive numbers indicate weight loss and negative numbers indicate weight gain. So we have 3 different diet programs: low calorie, low protein, low carbohydrate. So we have to check the difference, average difference, whether there is any significant average difference. So again, there are how many criteria are there to categorize this data? Obviously one criteria: low fat, low calorie, low protein, low carbohydrate. So that means diet. Different types of diet plans are the criteria. So there is only one criteria diet plan. So again we have a one-way classified data. So again you see we have to test the same null hypothesis: alpha 1 equals to alpha 2 equals to alpha k equals to 0 against not h naught. We'll again calculate the total mean, so the sum of squares between the groups, sum of squares within the groups, and here also N1, N2, N3, N4 are all same, that is 5. That means all the diet plans have been applied to an equal number of objects or subjects. Now we know how to calculate the whole thing. The whole thing has been summarized in this table, which is called ANOVA table. So again, this ANOVA table, we have the sources of variation, that is between groups error. The total variation is also there. The sum of squares are given there. We have to put down the sum of squares there. Degrees of freedom 3, 16, and the total is 19. Mean sum of squares and the F value. We have to put all these things in the ANOVA table. So one thing we can understand that this ANOVA technique can be applied in a wide range of situations. So we have to think where we should apply this ANOVA technique and how appropriately one should apply the ANOVA technique. And this is not the only ANOVA technique that we will consider. There may be more than one criteria for classifying the data. That means variability may be attributed to more than one factor. So we will discuss this in our next lecture. Thank you.